Okay, now we are going to learn about the pictures of quantum mechanics. We've already seen the representations of wave functions and operators in quantum mechanics. The connection between the various representations is provided by unitary transformations. And each class of representation, also called pictures, the representation is also called pictures, differs from others in the way it treats the time evolution of the system. The Schrodinger first we will see the Schrodinger picture, Heisenberg picture, and the interaction picture. These are the three pictures or representations that we discuss in this chapter. The Schrodinger picture is useful when describing phenomena with time-independent Hamiltonians, whereas the interaction and Heisenberg pictures are useful when describing phenomena with time-dependent Hamiltonian. First, initially, we will see the Schrodinger picture. In describing quantum dynamics, we have been using so far the Schrodinger picture, in which state vectors depend explicitly on time, but operators do not depend on time. Schrodinger picture എന്ന് പറയുമ്പോൾ നിങ്ങൾ മനസ്സിലേക്ക് വരേണ്ടത് the wave function or the state vector explicitly depend on time, but operators does not depend on time. So we can write IH cross d by dt of ket psi of t is equal to h ket psi of, that is IH cross dou psi by dou t is equal to h psi, where ket psi of t denotes the state of the system in Schrodinger picture. We have seen that the time evolution of a state vector ket psi of t can be expressed by means of the propagator or time evolution operator u of t0 as follows. We have already seen in the previous videos that ket psi of t is equal to u of t0 ket psi of t0. This is a transformation equation. We are transforming this state vector into this state vector, or we are finding the state of the system after time t. With the propagator can also be expressed as u of t0 equal to e power minus I of t minus t0 h by h equals. The operator u of t0 is unitary. We have already seen that, and the expression for unitary transformation, unitary operator is u dagger t0 u t0 or u dagger u equal to I, and satisfy these properties. The properties are u of t equal to I, u of t equal to I, u dagger t0 equal to u inverse t0 equal to u of t0 t, and u of t1 t2, u of t2 t3 equal to u of t1 t3. Then Heisenberg picture. In the Heisenberg picture, in the Schrodinger picture, we have seen the state vector depends on time, operator does not depend on time. So this is the equation of motion in the Schrodinger picture. And now we are going to the Heisenberg picture. In the Heisenberg picture, the time dependence of the state vector is completely frozen. Heisenberg picture is obtained from the Schrodinger picture by applying u on ket psi of t, and this h is the subscript h denotes the state vector in the Heisenberg picture. That means the psi does not depend on time t. So ket psi of t in Heisenberg picture, in the Heisenberg picture, psi of t does not depend on time. So it is completely frozen in time. So this state vector in Heisenberg picture is denoted by this subscript. The state vector can be represented in ket psi of t equal to this represented by this h, right? This superscript. The Heisenberg state vector can be represented by this subscript. Therefore, case psi of t h is equal to u dagger t cos psi of t is equal to, therefore we are using a transformation, an operator, u dagger operator uh, on a state vector psi of t, then we will get psi of 0. Psi of 0 means does not define the initial state of the system, where psi of t and u dagger t can be obtained uh, from this operator respectively by setting t0 equal to 0, u dagger t equal to u dagger t0 equal to 0, then e power ith by h cross, and ket psi of t is equal to u of t ket psi of 0, with u of t equal to e power minus ith by h cross. Therefore we can write ket psi of t, the same state, ket psi of th is equal to e power ith by h cross ket psi of t. As ket psi of h is frozen in time, we have d by dt of ket psi of h is equal to 0. Now we will see the expectation value of the operator. The bracket psi of t, a psi of t, this is expectation value of the operator. Then we apply the exponential expression of the operator, unitary operator. So we can write bracket psi of 0 e power ith by h cross a e power minus ith by h cross with psi of 0. Here actually what we are doing is that we are using the transformation equation of bra psi of t using this expression and cut psi of t using this expression. Then we can write bracket psi of 0 and this expression transform a into the Heisenberg operator. That is, this operator depends on time t. Therefore, we can write ah of t get psi of 0. So finally, we can write bra psi h. This h denotes the Heisenberg picture. The bra in Heisenberg picture, h of t get psi in the Heisenberg picture, where ht is given by u dagger t a u of t, that is e power ith by h cross a e power minus ith by h cross. We have seen that at t equal to t0, it becomes psi of 0 h e power 0 1 then equal to into get psi of 0. That means at t equal to 0, psi of 0 h equal to get psi of 0. That means Heisenberg picture equal to Schrodinger picture. So that means Schrodinger picture and Heisenberg picture coincide at t equal to t0. And we have seen that the operator in the Heisenberg picture, state vector does not depend on the time, but operator depends on time. So we can write the equation of motion in Heisenberg picture. Now let us derive the equation of motion that regulates the time evolution of operators within the Heisenberg picture. Assume that the air does not depend explicitly on time, that is dou A by dou t equal to 0, and since u of t is unitary, then we have uh, d a h of t by dt, where this operator h is time dependent operator. Then we can use the uh, we can transform this h into Schrodinger h using the unitary operator. So we can write dou by dt of u dagger t a u t plus u dagger t a dou u by dou t. Actually this is the form of differentiation. In which we write u dagger a u t, then we take the first function as u dagger, then second function as u of t, a u of t. We differentiate it, then we will get this expression. Then when we differentiate u dagger with dt, we will get minus 1 by I h cross u dagger h u dagger au plus 1 by, for this 1 by I h cross u dagger u dagger hu, which is equal to 1 by I h cross. We interchange this. We can write 1 by I h cross as u dagger hu, right? And therefore we can write dAh by dt equal to, this is the equation of motion in Heisenberg picture, dAh by dt equal to 1 by I h cross box ah h. This is the Heisenberg equation of motion, where dou psi by dou t is equal to 0. It plays the role of the Schrodinger equation within the Heisenberg picture. Since the Schrodinger and Heisenberg pictures are equivalent, we can use either picture to describe quantum system under consideration. Now we will go to the Dirac picture. It's also known as interaction picture. Is useful to describe quantum phenomena with Hamiltonians that depend explicitly on time. In this picture, both state vectors and operators evolve on time. So in interaction picture, both the operator and the state vector depends on time. Then we can directly go to the equation of motion for the state vectors. State vectors in the interaction picture are defined in terms of the Schrodinger state k psi of t by k psi of t in the interaction picture is equal to e power I t h naught by h cross k psi of t. If t equal to 0, we can write k psi of 0 I equal to k psi of 0. The time evolution of k psi of t is governed by the Schrodinger equation at t0. Then when we find the time evolution of k psi of t I, we differentiate this function. So we can write ih cross d by dt of k psi of t I is equal to, differentiate this function, that it is as the first function, then it is as the second function. Then we will get minus h0 e power I t h0 by h cross k psi of t k psi of t plus e power I t h0 by h cross into ih cross d by dt k psi of t. It is equal to minus h0 k psi of t interaction in the interaction picture plus e power I t h0 by h cross h k psi of t. where we have used now we consider h is equal to h0 plus v, that is h does not independent of time t, then v depend on time. We separate the Hamiltonian into Hamiltonian does not depend on time t and potential. Then e power I h0 t by h cross v is equal to, we can write as e power it h0 by h cross v e power minus it h0 by h cross e power it h0 by h cross is equal to potential in the interaction picture vi of t e power it h0 by h cross, which we potential in the interaction picture here, this is expressed here, and this equation of motion, becomes ih cross d by dt gets I of t interaction is equal to minus h0 gets I of t interaction plus h0 e power it h0 by h cross gets I of t plus vi of t e power it h0 by h cross gets I of t, or we can write ih cross d by dt gets I of t interaction I. These terms become cancelled. We will get vi of t gets I of t interaction. This becomes psi of ti. The Schrodinger equation. This is the Schrodinger equation in the interaction picture. It shows that the time evolution of the state vector is governed by the interaction potential. Then the equation of motion of the operator. The interaction representation of operator ai, it is given by in terms of the Schrodinger representation, which is equal to e power I h0 t by h cross a e power minus I h0 t by h cross, and we can show that d by dt a of t is equal to, differentiate this expression with time t, as this is first function, this is the second function, dou I by dou t is equal to 0. Then finally we can write 1 by ih cross box ai of t h0. നമ്മൾ സ്വന്തമായിട്ട് ചെയ്ത് നോക്കട്ടോ, വളരെ സിമ്പിൾ ഡിഫറൻസിയേഷൻ ആണ്. അപ്പോൾ നമ്മൾ ഡിറാക്കോ, ഷ്രോഡിഞ്ചർ, ഹൈസൻബർഗ് ഇന്ററാക്ഷൻ പിക്ചേഴ്സ് നമ്മൾ പഠിച്ചു കഴിഞ്ഞു. ഓക്കെ.